In this project, my objective was not only to minimize mean squared error, but to build a regressor that is statistically well calibrated, properly validated, and balanced in terms of bias and variance. My workflow emphasized the performance optimization alongside the rigorous model diagnostics. To improve performance, I first examined the distributional properties of the target variable, medical insurance charges. The target exhibits strong positive skew with a long right tail driven primarily by high-risk individuals, especially smokers, since MSE penalize the squared deviations. Extreme target value can disproportionality dominate the loss function. To adjust these heterodyties, the heavy-tailed behavior, I applied a log 1 plus 1, 1 plus 1, 1 plus y, a log 1 plus y transformation. This transformation reduces variance instability, linearize the multiplicative effects, and make optimization under an L2 objective more stable. After chaining, I reversed the transformation using an exponential explosion function to ensure predictions remaining in the original cost scale. Next, I implemented a full pre-processing pipeline to ensure consistent feature transforming and eliminate data leakage. Numerical variables were stabilized to prevent scale dominance, while categorical variables were encoded using one-hot encoding with unknown category handling. Embedding for processing with a pipeline ensured that scaling and encoding were learned exclusively from training folds during cross-validation, preserving methodological integrity. To systematically improve predictive performance, I compared three models representing increasing expressive power: ridge regression, gradient boosting, and the random forest. Ridge served as a linear baseline, while the ensemble method captured nonlinear interactions between features such as smoker states and BMI, using five-fold cross-validation. I evaluated each model's average MSE and stability across folds. Random forests achieved the lowest cross-validated MSE with the relatively low variance across folds, indicating both strong predictive capacity and stable generalization. Beyond selecting the lowest error model, I focused carefully on assessing model fit. I first verified consistency between cross-validation MSE and a separate holdout validation set. The holdout error closely matched the cross-validated error, suggesting that performance estimates were reliable and not overly optimistic. I then analyzed the learning curve to understand bias variance behavior. The curve showed that training error was lower than validation error, which is which is expected for flexible ensemble methods. However, the validation error plateaued at a stable level as training size increased, and the gap between training and validation error narrowed slightly with more data. This indicates controlled variance rather than pathological overfitting. The model exhibits low bias and moderate variance, but the generalization gap is stable rather than widened, which suggests that the model remains appropriately fitted within the current data regime. To further improve fit, I, I experimented conceptually with variance reduction strategies such as limiting tree depth and increasing minimal samples per leaf. These constraints would increase training error slightly uh, with with potentially reducing generalization gap. This reflects an international bias variance trade-off rather than passive acceptance of model behavior. From a methodological standpoint, the model can be considered well-fitted because cross-validation and holdout results are consistent. The learning curve does not show divergence between training and validation error as the sample size grows. The chosen model achieves the lowest generalization error among tested candidates. One key insight from this process is that model quality should be judged by generalization stability rather than training perfection. Extremely low training error is not the objective. Controlled validation error is. The workflow target transformation pipeline processing, model comparison, cross-validation, holdout testing, and the learning curve analysis ensures that performance improvements are both empirical and theoretically justified. Overall, my approach prioritizes the robust generalization and the principled diagnosis rather than leaderboard optimization alone. The final random forest model achieves strong predictive performance while maintaining stable validation behavior, indicating that it is appropriate fitted to the structure of the insurance dataset.